This video is on the derivation of the Michaelis-Menten equation. The Michaelis-Menten equation shown there on the screen in that bubble describes the variation of enzyme activity as a function of substrate concentration. So the variable Km in this equation is a compilation of rate constants called the Michaelis constant that is going to be unique to each enzyme and is going to be independent of enzyme concentration. The Km variable is going to describe the properties of the enzyme-substrate interaction, and it's going to vary for the enzyme that can use different substrates. So shown here in this equation, Km is equal to K minus 1 plus K2 over K1. Km is going to be an important characteristic of an enzyme-catalyzed reaction and is significant for its biological function. And then this variable is also going to be dependent on environmental conditions such as pH, temperature, and ionic strength. And then also in that initial Michaelis-Menten equation that we're going to be looking at today, the Vmax variable, or the maximum velocity possible, can be attained only when all of the enzyme, or the total enzyme, which is going to be shown there in that ET variable, is bound to the substrate, that capital S, as shown by this equation. Vmax can be set equal to K2 times that capital ET. The Vmax is going to be directly dependent on enzyme concentration, and it's going to reveal the turnover number of an enzyme, which means that it's going to reveal the number of substrate molecules that an enzyme can convert into the product per a unit of time when the enzyme is fully saturated. And so these two variables, the Km and the Vmax, are going to be important, and determination of these for an enzyme catalyzed reaction is often one of the first characteristics of an enzyme underneath, so they're going to be important. So the derivation of this equation is going to begin here with step 1 of this model. And in this, we have an initial enzyme capital E that's going to combine with substrate S to form the capital ES complex, and this is going to use a rate constant K1. Then that capital ES complex has two possible fates. It can either dissociate to that E and the S with a rate constant of K minus 1, or it can proceed to form the product P with the rate constant of K2. And then that ES complex can also be reformed from the E and the P by the reverse reaction with a rate constant of K minus 2. However, we usually simplify that reaction when we consider that the velocity of reaction at times close to 0, when there's not going to be measurable product formation and then no reverse reaction. So we actually take that out as shown in step 2, where that K minus 2 is removed. So then at this point, from step 2, we're going to want an expression that will relate the velocity of the catalyst to the concentrations of the substrate and the enzyme, and then the rates of the individual steps. So then our starting point is going to be shown here, where the catalytic velocity is going to be equal to the product of the concentration of the ES complex and K2. And so then at this point, in step 4, we need to express that ES in terms of known quantities. And so we're going to look at the rates of formation and the breakdown of ES given by those two shown there. The rate of formation is set equal to the ES equal to the K1 times the E and the S, and then the rate of the breakdown of the ES is going to be the K minus 1 plus K2 over the ES. So then at this point, we want to simplify matters further. We're going to use the steady state assumption. And so in a steady state, the concentrations of the intermediates, in this case the ES, are going to stay the same even if the concentrations of the starting materials and the products are changing. And so we're going to set the right-hand sides of that rate of formation equation and the rate of breakdown equation equal, which is going to give us, shown here in number 5, that first part, which then we can just rearrange as that arrow shows to that second part, and that should actually say, in that final equation there of step 5, that should actually say the E times the S over ES is equal to that K minus 1 plus K2 over K1. So moving on, after we have rearranged it to that equation number 5, we're left with equation number 6, which was found just by simplifying and defining a new constant, the Km, as we talked about at the beginning, again called the Michaelis constant, shown here. And then by inserting this equation that we have here just into the previous one of step 5 and solving for the ES is going to give us this equation number 7. And so at this point then we're going to look at the concentration of the uncombined enzyme E as being equal to the total enzyme concentration, that capital ET minus the concentration of the ES complex. And this is again because the substrate is usually present at much higher concentrations than the enzyme. So the concentration of the uncombined substrate S is very nearly equal to the total substrate concentration. So all of this process is going to give us this equation of where we are at this point solving again for that E. And then we are going to substitute that equation into number 7, which is going to give us this equation. And so at this point, all we're doing then from step 9 is we are going to solve equation number 9 for the ES, which then will either result in either of those two listed in number 10. Again, that's just for solving for number 9 in terms of the ES. And so from step 10 then, we are going to substitute the expression for the ES into our original equation of number 16, which is not shown on the, not equation 16. Equation all the way back at the beginning, our number 3, which was that VO is equal to the K2 times the ES. When we substitute this expression number 10 into that original equation, we're left with this, solving again for that VO, or the velocity. And so at this point, from step number 11, the maximal velocity, the Vmax, is going to be obtained when that catalytic site of the enzyme is saturated with a substrate. That is when that ES can be set equal to the ET. This is going to give us this, just showing what that process looks like. And so then our last step, last but not least, we are going to substitute this final Vmax equation into that VO as shown there, which is going to yield us our final equation, which is known as the Michaelis-Menten equation.